Hi everyone, this is Asma Mushtaq from the W Vibes, and in this video lecture we are going to derive the value of the electric field intensity of a line charge according to the Gauss's law, and you will see that the derivation is quite simpler as compared to we did in the previous lectures using the Faraday's law. Alright, so let's assume that we are having a line charge which is actually positively charged and it is placed along the z-axis. Fine. Around this line charge, the first step is to determine or to imagine a closed Gaussian surface, and the property of the Gaussian surface is such that the electric flux density at each point on that surface must have a constant value. Alright, the second property is that the ds component either should be tangential or it should be normal to that surface. If we choose a right circular cylinder of the radius rho that extends from 0 to L as shown in this figure, then we can see that here are three types of the Gaussian surfaces involved in it. The first one is the top surface, which is actually pointing upward. The second one is the bottom surface, which is actually pointing downward, and the third Gaussian surface is actually the cylindrical surface, which actually pointing in the direction of the rho or the radius. Now coming back to the basic formula of the Gauss's law, we see that Q is equal to D dot ds. Since here are three surfaces involved, so that's why I can split the integration on the top, then on the bottom, and finally the cylindrical surface. So it becomes, or it is split into three surfaces. Okay, so the expression is d dot ds, d dot ds, and d dot ds. All right, now we can see d is the electric flux density, and this surface area also has a particular direction whose direction is always normal to the surface. Okay, these two are the vector quantities, and we are going to take the dot product. Since we have assumed that the flux density should be constant, okay, on that surface on the top, if you look, then the value of the ds is actually along the radius line on this cylinder, while the surface area is pointing upward. So the angle between d and ds is actually of 90 degree, because this is the value of the ds which points towards the radius or along the radius, while surface area is pointing upward. That's why this expression or this dot product becomes 0, because d dot ds is actually equal to the magnitude of d, magnitude of ds, and the cos of the angle in between them, and cos of 90 is equal to 0. So this expression becomes 0, then plus. If you look at the bottom, the same scenario is true, because the ds is pointing downward. This is the direction of the ds surface area, while the flux density is pointing towards the radius, and the angle between them is of 90 degree again. This expression also reduces to 0, and the only thing that is left behind is the d, which is actually constant, and we can take it out from the integration, and we will integrate only on the surface area. Fine. The next step is to determine the surface area. Since we are having a cylinder of radius rho, let's assume that I consider a small patch of it. Fine, this is ds. Okay, this vertical side, if I draw it separately, I can see that this vertical side actually represent the change in dz, while this curved side has the length according to the formula s is equal to r d theta, where r is the rho and d theta is actually d phi in the cylindrical coordinate system. You can also watch my lecture where I have explained completely about the cylindrical coordinate systems. Okay, so the surface area becomes ds, which is equal to rho d phi dz. Okay, z varies from 0 to L as we mentioned earlier. Now let's just substitute the values in the above expression. You will get rho d phi dz, and since two derivatives or the differentials are involved, so two integrals will be considered. On the left hand side you are having q, while on the right hand side you are having ds. Then you have to integrate on the d5, rho is also common, you can take it out. Rho is constant, so you can take it out from the integration, and here you will integrate from 0 to 2 pi and then 0 to L dz. So this becomes rho ds, and here you will get the phi, where you have to apply the limits from 0 to 2 pi, and similarly here you will get z, where you have to apply the limit from 0 to L. So q is equal to rho ds, then this becomes 2 pi, and here you will get the value of L. Okay. On further simplification, we can see that ds is equal to, if you let it be on the right hand side and you take the remaining terms on the left hand side, it becomes q over 2 pi rho into L. As we know that q over L can be defined as the charge per unit length, which is represented as the line charge density, and its symbolic representation is rho L. So let's just substitute q over L by rho L, and ds becomes, ds is equal to rho L over 2 pi rho. Okay. Also, we know that d is equal to epsilon into E. So from here, E vector is equal to d over epsilon. So let's just divide this expression by the epsilon. So you will get from here E is equal to rho L over 2 pi rho, d divided by epsilon, and epsilon is divided, and obviously it was acting along the radial line. So don't forget to add the unit vectors always. Okay. So you can clearly see this procedure is quite simpler as compared to the previous one, where you have to perform the complex mathematical calculations. If you like the lecture, please like this video and share and subscribe. Thank you for watching.